After that, we solved some problems as well. Uh, we were not able to discuss about forward converter, so in today's session we will start forward converter as well. So let us start the discussion. Any doubt from last class? Okay, so let me present my screen first. So I hope my screen would be visible. So we observed in the last session that our flyback converter works as a buck boost converter, right? With isolated supply. There is an isolation between input and output. Okay. So uh, we discussed one problem. Let me go back to the problem. Yeah. So we discussed, I think this one. Yeah. 24 volt was the supply and output was 5 volt, and we needed to compute the value of duty ratio and average value of inductor current, magnetizing inductor current, maximum and minimum value of that magnetizing inductor current. So uh, an extension to that problem we will see today. Let me bring back the problem here. So in that problem, the resistance was given about 20 ohm, or sorry, 5 ohm. Okay. This is the resistance value. 5 ohm was given. Okay. Now in the extension problem, it is being asked that what will happen if we increase the value of resistance up to 20 ohm. Okay. So now R new. Yeah. Anyone wants to say something?
Sir, in the last case
Mm-hmm.
of the problem,
Yes.
sir, we have calculated that IL magnetizing current.
Mm-hmm.
Sir, in a flyback converter,
Yes.
instead of transformers, we used couple inductors. So, is there a possibility of a separate inductance called magnetizing inductance there?
See, in a transformer, there will be a magnetizing inductance, right?
Yes, sir.
Yeah, but do not denote that as a separate magnetizing inductance.
In flyback
Sorry?
or in transform? You are saying in transformer.
No, no, in flyback. Or even in an ideal transformer also, we remove that because of the reason that we do not need magnetizing inductance there.
Okay.
So just like that, we are representing an ideal transformer here. Okay. But in flyback converter, we are connecting and magnetizing inductance separately. As you might be able to see, let me bring back the figure. Yeah. So here we have connected and magnetizing inductance separately uh, s- to visualize in a better way. Just that. So, what is your specific doubt in the problem that we should not use this magnetizing inductance or what?
No, sir. Actually, the transformers only have magnetizing inductance.
Hmm.
Whereas in flyback converter, this is not a transformer. They say it is a coupled inductor
Why you are saying so? Coupled inductor?
because it stores energy.
Yeah,
In
that's right. Yeah.
uh, since it stores energy, it can be called as a transformer. It is a coupled inductor.
Okay. So, do you have any reference for that, or you have analyzed by yourself?
No, sir. In the other PMRF sessions, sir told
Mm-hmm.
that this is a coupled inductor which stores energy.
Okay.
So it can't be treated as similar to a transformer.
Okay.
My doubt is transformer only has a magnetizing inductance.
Mm-hmm.
We are using a magnetizing inductance for the coupled inductor also.
Mm-hmm.
So is that
Okay.
yeah,
No.
that is
First thing is that we are using here the concept of, oh, sorry, let me put it that way. We are transforming the voltage from secondary to primary side or primary to secondary side, right?
yes.
And we are not bothered about any other thing like energy, what are the energies stored in that in this one, in this portion. If it would have been a coupled conductor, we would have analyzed with the way how we deal with coupled conductor. But do we or have we considered it as a coupled conductor? I haven't seen anywhere in any textbook as of now. You can see it as a coupled inductor. That's another thing. But you cannot call it, right? Because transformer is nothing but at the end of the day, it is also a combination of resistance and inductance, right?
Sir, but in flyback, when the switch is on,
Hmm.
the secondary side power flow, the current is not flowing on the secondary.
Yes,
Only
correct.
when the switch is off, the current is flowing on the secondary.
Yes.
So when the switch is on, it is storing the energy, and when
Hmm.
the switch is off, it is giving that energy to the secondary. So
Right.
which means it stores the energy.
Yeah.
Uh, okay.
Yeah, it is it is working as an inductor, as an conventional inductor, right? But see, energy is being stored at this stage, right? Now when switch is open, the energy from this inductor or current from this inductor will free will through this winding. And whatever current will flow here, that will get induced here, right? So where does it happen? In transformer, it doesn't happen. We do not transform the current and voltage from primary to secondary.
Yes, we will.
Someone
We will.
can call it as an inductor, that's no issue, but it is working ideally as a transformer, right?
Okay.
Okay.
Okay, sir.
Any other doubt? If you refer any textbook of basic magnetics, so there you will see a
Okay.
transformer is modeled with couple of inductors. So that's another way. I am not denying that it is not an inductor, but at the same time, it is most appropriate to call it a transformer. That's it. Yeah.
Sir,
Yeah, yeah, please go ahead.
adding to this point, in the lecture it was told that a transformer is a power transfer device and there is an inductor is an energy storage element.
Okay.
So there the design we use, the mu will be less, permeability will be less since it so that energy storage is more in the case of inductor. Inductor is an energy storage element.
Yeah, you can. Yeah, see, both way of putting it is correct. The thing is, we are designing here this magnetizing inductance to
But this is
this.
a magnetic inductance and these two are these versus transformer.
Yeah, so magnetizing inductance will decide how much energy it should store, right?
Yes, yes.
Yeah, and at the end of the day, we have to transfer that energy from primary to secondary.
To secondary.
Yeah, and that transformation can be done only with the help of
Only through
transformer.
transformer.
Yes.
Okay, okay.
Yeah. Even you will see that in forward converter, I don't think there will be there will be any magnetizing inductors there. But there also this process is happening, right? So whatever energy, let us suppose that transformer winding, suppose in transformer winding itself, there are sufficient number of turns, then that would be suffice to store the energy whatever is required. So we will see in forward converter what happens, and we will continue this discussion.
Okay, sir.
Yeah. Yeah, so I was about to discuss that from last problem, when we are increasing the value of resistance from 5 ohm to 20 ohm, right? So what will happen? So first thing we can observe that as soon as we increase the load demand uh, from 5 ohm to 20 ohm, our current will reduce for the same voltage at the load side. Okay, and how much it will reduce? Are you getting any idea where we are heading with this increment of resistance? What we are trying to achieve with this kind of problem? So basically, when we are increasing, yeah, go ahead. Someone wants to speak.
No, sir. Are we going to find some minimum loading or maximum loading?
Yeah, something like that. We will try to find out the boundary condition, or whether in this scenario our converter is operating in continuous conduction mode or discontinuous conduction mode. So that would be our objective to find it. Okay, we have
Oh,
done it
based
for
on
the,
this R.
yeah, because we have increased now the value of resistance. So uh,
Okay.
for the same amount of voltage, our current is going to be reduced, right? So
Okay.
for that purpose, and if our current that will flow through the inductance, and if it will reduce from certain level, then there are possibilities that it might go in DCM. So that we will try to compute. So, should I bring all the previous data? Yeah, it would be better if all the data would be here. We might have forgot. So this was the initial data uh, with the help of what we solved in the last session. So yeah, so first thing first, we have V naught and Vs, and we are trying to find out whether this converter will be in CCM or DCM. If, let us assume, if our minimum value of inductor current is less than 0, means it will try to go in negative. It means the 0 value is being touched earlier than the time period. So we can conclude that the converter will be in DCM, right? So we will try to compute IL minimum, and it's when its value will be less than 0, then we can say that it is in DCM. Otherwise, CCM. Okay. So we know that IL minimum value would be IL average minus del IL by 2, right? And IL average we have computed earlier, and if not, at any point of time you can easily compute it. So IL, if you will try to visualize the converter, let me bring the converter here on the screen. so that you can visualize it easily. Yeah. So this is a converter, flyback converter. Okay. Whatever the value of source current, okay, during on period of the switch, when the switch is closed, then whatever the value of source current, that will be the same of inductor current. Okay. So ILM average we can write as, sorry, ILM average we can write as IS by IS average by D. Okay. And of course, when switch will be off, our magnetizing current will flow through the winding and it will transfer its energy to the secondary. Right? Now, there must be some relationship between IS and I naught. Okay. So, as we have found out the relationship between output voltage and input voltage, we can easily compute the relationship between output current and input current. Okay. So, if I try to write IS in terms of I naught, then I can write it as IS by I naught is equal to VS by V naught is equal to D by 1 minus D into N2 by N1, right? So let me put it in expressions. So Is is equal to I naught into D by 1 minus D into N2 by N1, okay? And D is here already. So this is the value of our average current, and I naught, if you know, I naught will nothing but the V naught by R, and I I think we know the value of V naught, so that should be fine, and this D and D will be cancelled out. We can further write it as V naught by R into N2 by N1 into 1 by 1 minus D. Okay. I hope it is fine till now. After that, we know the value of V naught, that is 5 volt. Okay, so V naught value is 5 volt and R we have increased to 20 ohm. So let me put it here, 5 volt divided by 20 ohm, and N2 by N1. N1 by N2 was 3, so N2 by N1 would be 1 by 3. Okay, and we left 1 by 1 minus D, so 1 by 1 minus D, I think we have computed the value of D, or it must be given somewhere. So D was 0.385, I think we have calculated earlier, and you can compute any time. V naught by Vs is equal to D by 1 minus D into N2 by N1. So with that expression, let us assume we have computed D as 1 minus 0.385. Okay, so this is the value of D, 0.385, and when we compute it, we will get 60 into 1 minus, so it is coming out to be something 0.1355 ampere. It means 135 milliampere. Okay, so we are done with the average value of magnetizing inductance. Now we need to compute the ripple in that magnetizing inductance, that is del ILM. So when this switch is closed, okay, we can apply the voltage equation across this inductance. You will see that VLM is equal to L del ILM by, we are talking about when switch is closed, so that we can write as dt, right? So it will increase from IL minimum to IL maximum. So we write that variation in terms of del ILM. So I can write it here dVs by FLM, and we have the value of D as 0.385 and Vs is equal to something 20 ohm or 24 volt. So Vs is 24 volt, and F frequency value we have, that is 40 kilohertz, and LM LM I think we computed in the last session. So
So it is given, I think, 500 microhenry. What is it?
how much? Could you please repeat it? 500 microhenry. Yeah, it is given here. Yeah, you pointed it correctly. It is 500 microhenry. So we will put it there. So we can write at zero point 0.5 millihenry, and it should be plus. So this kilo and milli will be cancelled, and we will compute the value. What will come out? It will be 0.385 into 24 divided by 20. So it is 462 milliampere. Okay, I hope it might be right. And now we can see that,
Yes, sir.
yeah, thanks. So IL minimum was IL average, that is 135.5 milliampere minus 462 by 2, right? Del IL by 2 milliampere. So it will come out to be 135.5 minus 462 by 2. It is 95.5 amperes in negative, right? However, inductor current will never go in negative. It just signifies that inductor current will be zero before the time period. So we will be convinced with this kind of result that our converter is in DCM, right? So that's what we needed to compute or identify first, and after that, if it is going in DCM, then what should be the minimum value of inductance we can provide so that it should maintain at the boundary at least, right? So for that purpose, we need the value of critical inductance. Okay. Did I derive the expression of critical inductance in the last class? Anyone able to recall that? Anyone?
Not sure, sir.
Okay. So it means it might not have been derived. So okay, so let us derive that.
Sir, here we are talking about this IL in this problem.
IL, we computed minimum value of inductor current so that we first identify the whether the converter it is in CCM or DCM. After that, we need to find out the value of critical inductance.
Yeah, okay. Sir, but this L is, uh, it
500.
is the, okay.
It is given 500 microhenry. Now, can we redesign so that it can go in at the boundary
So
of?
that, okay, only, we are talking about only the current flowing through this magnetizing inductance.
Yeah, because that's
Okay.
only in our hand, right? So
Hmm.
for that purpose, we are dealing with magnetizing inductance. Yeah.
Okay. Sir, in the in the last, in some of the steps, yeah, we write that IL average equal to uh, IS average by D.
Yeah, I have written it here. Yeah.
Sir, in this step, IS flows only in the on time of the switch.
Yes,
Uh, so D into ILM average is
IS average.
IS average. Okay.
Yeah.
Okay, sir. Yes, sir. Okay, sir.
Yeah. Okay. So let us proceed with the derivation of critical inductance. Okay. So we do not have to do much from this point since we know the expression of ILM average, oh, sorry, ILM minimum, and we have to just equate that expression to zero, right? So if we can do that, ILM minimum is equal to zero, then with this condition, the value of inductance we will get, that would be our minimum inductance. Okay. So let us go ahead with this. Let us get that expression first. So it is here I naught into n2 by n1 divided by 1 by d. So I naught into n2 by n1 into 1 by 1 minus d. It is ILM average minus del IL by 2. So that we know anyway, dVs by FL by 2. And with this condition, it will be critical inductance. And now we have to equate it. So we will get L critical in terms of n2 by n1 I naught 1 minus d into, sorry, I forgot the factor of 2. So it will be 2 into f to dvs, right? I think I have written it correctly. Some mistake is there.
Sir, these two are ILM max and del IL.
This is ILM average and this is del IL by 2. Let me write it just for the clarification. This is del ILM by 2. Got it?
Yes.
So dVs by 2f, okay, and I naught into n2 by n1 into 1 by 1 minus d. I hope it is right now. And if we simplify it, we will get dVs by 2f I naught. Okay. n1 by n2 into 1 minus d. Okay, so up to now this is fine, but one factor of Vs by I naught. Okay, if somehow I can convert it into V naught by I naught, it would be more easy, right? We do not need to see the value of Vs and I naught because these are kind of controllable and variable sort of thing. We can vary it. So we should be able to write in terms of resistance so that at any times we can see the value of resistance since resistance is fixed generally, and we can compute the minimum value of inductance. So we know that V naught by Vs is nothing but d by 1 minus d into n2 by n1. Okay, so Vs, if we will try to write in terms of Vs, sorry, Vs, if we try to write in terms of V naught, so we can write it as V naught by V naught into 1 minus d divided by d into n1 by n2. Okay, so if you will simplify, or if you just plug in this Vs value here, you will get the value of L critical in terms of resistance, because once V naught will come here and I naught is anyway there present, so V naught by I naught should be R. So let me just plug in that value. V naught is equal to d by 2f n1 by n2 into 1 minus d. Now I will bring back the value of Vs in terms of V naught. So V naught by I naught into 1 minus d into n1 by n2. Now you combine, so n1 by n2 and n1 by n2, it will become n1 by n2 square. So, and this term as well, 1 by 1 minus d into 1 minus d, it will become 1 minus d ka square. So n1 by n2 into 1 minus d square and 2d by 2f. Okay, so d by 2f, and this v naught by I naught would be r. So this r will be here. So that's all. That is the value of our critical inductance. Okay, so I think some D has been carried out all the way. That should not be present in this expression. So you just verify it once. I think this D has been carried out. It should not be present in the expression. If we will just go through once. So dVs, somewhere it has been carried out. Let us go from this step. So dVs by FLM.
Sir, I think from that IS average step it has been.
Okay, let me see the IS average step. Okay, IS average. Okay, yeah, I got it. In IS average, I took that D value. So ILM minimum was ILM average divided by D. ILM divided by D. ILM average, let me see. Okay, so I think you just see it at your own and let me know if there is any I naught into D by 1 minus D. So yeah, I naught into N2 by N1 divided by 1 minus D. So I naught into, yeah, it is fine. Now L critical AD Vs. Here also it is fine. Here also it is fine. So Vs is equal to V naught into 1 minus D divided by D. Yeah. So V naught, v, when I plug in the value of Vs, I did not divide it by 1 minus D. So this D, let me show it to you. This D did not come at this point. So this D should come at here, and this D and D will be cancelled, and it will be R by 2F. So any confusion? Should I clarify it once more?
No,
Okay,
just
so yeah, I hope it should be fine. So that is the value of critical inductance in case of flyback converter. If you want to remember this expression, you can do what, where will that help? That will help to identify the converter quickly, whether it is in CCM or DCM. So once you see the data and you just, if you remember this expression, you just plug in all those value and you can find it out that whether the given inductance is less than this critical inductance or more than the critical inductance. So if it is more than critical inductance, it means your flyback converter is in CCM, otherwise it is in DCM. So that's where it will help you. So let us proceed with some other converter, that is forward converter. Okay, I hope there is no doubt related to flyback converter. If it is there, we can clarify it now. Okay, one more thing I wanted to derive. What will be the value of V naught and what will be the ratio of transfer function that V naught by Vs and where it will change, so in DCM mode particularly. So let me equate the power of input and output. So from that we can easily derive. So we can write here to balance the power Vs Is is equal to V naught I naught. Now it is okay. So as we know Is in terms of Vs and all, so we are just concerned with V naught by Vs here, the ratio of V naught by Vs, that will be Is by I naught. Okay. So if somehow I can replace the value of Is in in terms of V naught and Vs, so that we will not get the expression of Is and I naught in the expression. So it should be just the transfer function should be just the combination of duty ratio, resistance, inductance, frequency. What are the parameters generally given? So Is we can write it as okay in discontinuous converter half into del ILM, because whatever the ripple in the inductance, if you will see, so it is your T time period, so it is del IL. So it is del IL. So half into del ILM into dt, right? Is is equal to ILM by D, right? So, sorry, ILM into D, or let us tell me in graphical form, this is your dt, this is t, and this is the waveform of is. So I hope it is better to visualize now, right? So is is conducting, or the waveform of is will follow the waveform of magnetizing inductor current till the switch is on. So it is its average value will be the average value of source current. So its average value will be half into del ILM into dt divided by t. So if we cancel it, this t and t, so we will be left out with half into del ILM into d, and we all know the value of del ILM. So half into del ILM is dVs by FLM into d. So it will be d square Vs by 2 FLM, right? So we converted the average value of Is in terms of D, VSF and LM, and that is not dependent of some other thing. And I naught, we know that I naught is V naught by R. So I naught also we can convert in terms of Vs and V naught and circuit parameters. So it is V naught by R. And now we will plug in these two values in this expression. V naught by Vs is equal to Is by I naught. So V naught by Vs is equal to Is by I naught. So first I will write the value or magnitude of Is. Okay. So d square Vs by 2 into FLM. Okay. And I naught as a V naught by R. Okay. So this V naught by R, if we will take it on the left hand side, so and this Vs, if I will take it as right hand side, so V naught square divided by R is equal to d square Vs square by 2FLM. Okay. And now again, if I will transfer V naught by Vs, the whole square is equal to d square into R by 2FLM. And now the ratio of V naught by Vs is equal to d into under root R by 2FLM. So the expression of transfer function of this converter during DCM mode is completely different from the CCM mode. As you are able to see here, no terms of turns ratio is coming in the picture, right? So that's the thing here I wanted to discuss. Any question on this? If not, then we will proceed forward. Okay.
Sir,
Yeah, go ahead, please.
in the DCM mode, in flyback converter, the gain seems to be less than the CCM. Is it right?
I don't
because
think I will have to again compare, but generally in DCM mode, what happens, average value of this transfer function is higher than whatever we achieve. So just let us verify. We have solved two problems, right? So we have both the data. So we will see the ratio of V naught and Vs in both the cases. So that should be fine. And that
yeah,
would
because
generalize our assumption. Okay. So, uh,
LM usually will be ideally it is infinite LM.
hmm,
Usually, practically also it will be very higher. And
okay.
if you have the switching frequency also higher, then V naught by Vs will be lesser. That's my understanding.
Yeah, your way of putting it is correct, and I think it should be. So I think we can verify it here just now,
Yeah,
and,
yes, sir.
and that should be fine. It will be just 2 minute work. So in DCM, V naught by Vs is we had all the value. So D was 0.385, okay, and R was 20. 2 into F frequency was 40 kilohertz as far as I remember. F is 40 kilohertz and Lm was given 500 microhenry. Yeah, so as we can see, it is depend just the value of R has been changed from CCM to DCM. So this R value, okay, it is less in case of CCM. So what will happen? You tell me.
Sir,
Yeah, go ahead, please.
what is the question, sir?
Yeah, I asked that here in CCM and DCM, all parameters are same. Only the value of resistance has been changed, right? So I think we will be able to. Okay, let's forget the question. Let us complete this exercise first. 20 divided by 2 into 40. This is into 0.5. So it is
Coming up to be 0.272.
0.272, 0.385 divided by I am getting 0.544.
The root we have to take.
Yeah, after including that under root value, 20 divided by 2 into 40 into zero point 0.5.
Actually, it comes out to be root of zero point 0.5. So it is 0.707.
Yeah, it is right. Till this point it is correct, I hope. No, this expression.
Yes, correct, sir. That is the answer, sir.
Okay, so yeah, it is 0.272. That's what you are getting?
Ah, yes.
Okay. And in CCM, V naught by Vs was N2 by N1 into D, that is 0.385 divided by 1 minus 0.385, and N2 by N1 was 1 by 3. Okay, so let me. So it was 0.208. Am I correct?
Yes, sir.
Okay, so you can visualize it here that in DCM the value is higher. So generally it comes higher, but I just wanted to show that is it true for every case or not. So as you see that your converter enters into DCM, basically what happens that your negative component of voltage, the conduction period of negative component of voltage, if you see the inductor voltage profile, that will be reduced, right? So because of that, you will get less reduction in voltage.
Oh, because of that output average increases.
Yeah, that's because average of your output voltage will be higher. So again, so for DCM case, we have derived that V naught by Vs. You can use it anywhere. As soon as you verify that your converter is in DCM, you can write this expression. Okay. So now let us move ahead with forward converters.
Sir, in CCM, the gain is irrespective of resistance, load resistance.
In
So independent of load resistance.
okay.
So so it means whatever load we connect, we'll get this gain.
No, actually that is not true. See, V naught by Vs is gain. Okay. And as you increase the load, it means you have increased the value of resistance. So either you increase the load with the increment in load resistance or you reduce the current, right? So a-
Uh,
if you have increased the resistance and you have kept fixed the current, then your V naught will higher, right? You cannot vary all the parameters. You will increase the load resistance, you will increase the current, then again, in that case also V naught will be greater. So, your question was when you are increasing the resistance, then what? Can you repeat it, please?
no, sir. This the gain in CCM
Uh-huh.
seems to be independent of load resistance.
Yeah,
So
okay, so,
can
go ahead.
can we keep any value of R so that this gain will remain same?
No, just now we saw that with the
Yeah, yeah.
increment in resistance, we will
Yes.
have to take care all. Actually, you are not able to see, and that is inherently included in this expression. So V naught and Vs, if you see, it will be included because V naught is dependent on load current, load resistance inherently. So this V naught, if you regulate, then it is fixed. Otherwise, it will vary. As soon as if you will increase the resistance, you saw or we saw that our load current has been reduced. Okay.
So when the V naught becomes unregulated after some point, then I think R comes into picture.
Yeah, then R is anyway it is there, but that will play a major role. Okay, so if there is no further doubt, so we can proceed with forward converter. Okay. So it is another magnetically coupled DC-DC converter. Okay. And its operation is similar to other converters. So let me draw first the circuit. Okay. I think some message in the chat box. Discuss on problem 9 of current week's assignment. Okay, we will discuss it definitely at the end. Okay. Current week's assignment means you mean week, which week? Let me see. Problem 9 of current week assignment. That might be based on
Yeah,
mag
magnetic, sir.
magnetics. Okay, I will see the problem and at the end we will try to solve that. Okay. Here it is your primary winding turns. This is magnetizing inductance. Okay. And here I am drawing in different ways. If, okay. So this is N1, this is N3, and now I will draw secondary side which is called. So if I will, so primary and tertiary winding is connected conductively as well as inductively. Okay. And secondary side is connected conductively only. So this will be considered as D1 and this tertiary would be considered as D3. And the dot polarity will be such that here it will be N2 number of turns and this is the dot convention of this transformer. So after that, its structure will be similar to our conventional buck converter. Okay. Uh, After this point, after this node, let me denote this node, and here capacitor is connected similar to the buck converter and the load is connected. Okay. Okay, fine till now. No, any doubt, yeah. And V1 will appear here. Okay, and V3 will appear here, and V2 will appear here. Any doubt in the circuit first? Okay, if no doubt in the circuit, so the purpose of the three windings are first we need to transfer the energy from magnetizing inductance to the output side. Okay, so winding 1 and winding 2 that will be used in the transfer of energy from primary to secondary side. Okay, winding 3 is used to provide a path for the magnetizing current. Okay, when this switch is open, then magnetizing current will try to flow through the tertiary winding and this primary winding. Okay, so it will provide a path for the magnetizing current. when switch is open, and the magnetizing current must reduce to the value of 0 before the start of next switching period. So we must reset the core flux, okay, of magnetizing inductance before the start of every next period. So that's the purpose of our tertiary winding. Okay. So if
Can you repeat this once?
yeah, so the purpose of our this tertiary winding is to reduce the magnetizing current to the value of 0 before the starting of next cycle or next period. So every time we must reset the value of flux in the core, it should be 0 before the starting of the next cycle. Okay, is it fine now?
Okay, sir. Okay.
Yeah. So, okay, one thing is not fine here in this circuit. I think this D3 should be connected to, it is fine. Actually, I tried to redraw on my on so that I can simplify the circuit. So,
This is D3 bottom has to remove, yes.
yeah, D3 should be connected to supply here.
Hmm. Then between LM and the ground bottom rail, a switch should come.
Yeah, now I think it is fine. Yeah. So the upper terminal, one terminal of tertiary winding will be connected to the positive side of our primary winding, and the lower terminal of tertiary winding should be connected to the negative side of supply basically. Okay, so that when this switch will be closed, okay, when this switch will be closed, this D3 will see the value of Vs along this diode, and it will make it in reverse bias kind of situation, and our tertiary winding would not conduct during that time. But as soon as our this switch gets open, then this magnetizing inductance should transfer its energy through the primary winding and the tertiary winding, and in that case it will be connected to the D3. So we will see what will happen so that our tertiary winding will get forward bias. Okay, so because how I am saying that our tertiary winding will become forward bias, that will be much clearer when we will see the expressions of this voltage V3 in terms of V1 and V2. So let us analyze once. Let me first copy this circuit so that every time, yeah. So when the switch is closed, this V1 will be equal to Vs, okay, and this V1 will be reflected to V2, okay, and V2 will become by turns ratio V2 by V1 is equal to N2 by N1. We can write it conveniently. when V2 is positive, now this diode D1, it will conduct, okay, this will conduct, and this diode D2, it will be reverse biased, and our inductor, this Lx, it will be charged till the switch is on, right? Since V2 is positive, till now at least. And now, what will happen to V3? So, V3, we can see V1 dot is this. So, whatever the magnitude of V1 with respect to this dot, the same polarity of V1 will, sorry, the same magnitude of V1 will be reflected to V3 with the multiplication of turns ratio. Okay. So V3 will be equal to V1 into N3 by N1. Okay. But since we have given the polarity in such a manner, our V3, the positive terminal of V3 will appear along the cathode of the diode. So that is making it reverse bias. So we have designed it in such a manner it will intentionally reverse bias the diode D3. Okay.
Sir,
Yeah, go ahead, please.
here the scaling of V3
Hmm.
can be done if we want to operate this forward converter more than 50%,
Mm, V3,
because V3 will appear, the voltage appeared across the V3, we can make it more, the stress on the switch will be higher, but
yeah,
we can reset it in shorter, because the whole second product is going to remain same. Only the negative peak appearing on V3 will be larger,
hmm,
suppose.
yes,
Then,
yes.
then we can operate more than 50%. I think in this configuration.
Yeah, I think you can proceed with that. Yeah. If you will increase the value of N3, you are saying you can double the value of N3
Yes,
so that you can double the
but
value of V3.
uh,
Yeah.
the stress on the switch will be more, but we can reset it earlier
Yeah,
with a larger V voltage across the switch. Okay.
definitely. Yeah. But you have to pay price in terms of switch
Of
rating.
switch rating, yes, yes,
Yeah.
definitely.
Yeah.
So here the advantage of that will appear. If the voltage of smaller voltage forward converters are there, then we can take that type of risk.
Definitely. Because uh, current will die down as large our voltage across that winding.
Winding, yes.
So let us see the VD3. What will be the rating of VD3? So if you apply the KVL, so you will see,
Sir, one doubt, sir.
sorry,
One doubt.
yeah, go ahead, please.
Here we have an expression V2 equal to V1 into of N2 by N1, no?
Yeah,
How an power is transferred from V1 to V2, sir? Here and V3,
yeah. So see,
D3, here diode is not conducting, D3,
huh,
when switch is closed.
okay. So this is a primary winding, right?
Yes, yes, sir.
And this is a secondary winding.
Reminding.
Huh. So they are connected inductively.
Okay.
Okay. So
Okay.
as long as they are connected inductively, you can apply the turns ratio or transformation ratio.
Okay, okay.
Okay. So let us compute the stress of diode, how much it will it will handle when this kind of scenario will be there. Okay. So we will apply the KVL in this loop. And let me take the black color. So okay. So Vs we can write Vs plus V3 since we are going from negative to positive. So Vs here again we are going from negative to positive. So V3 minus, since in D3 we are, let us assume this will be conventional polarity of any diode. So positive at the side of anode and negative at the side of cathode. So we can write VD3 is equal to 0. Okay. With this expression, we can get the stress of VD3, that will be minus Vs plus V3. And if you try to write Vs in terms of, sorry, V3 in terms of V1, V1 N3 by N1. So this VD3 must be able to block this much voltage, first Vs and then V1 into N3 by N1. Okay. So whatever the value of V1 that you will get, and that is what? V1 is nothing but Vs, right? During turn on. So when V1 is Vs and typical value of N3 by N1 is nothing but 1. So number of turns generally we keep as N3 by N1 is equal to 1, so that we do not need the higher amount of mm, voltage blocking capability of the switch. Let me write in terms of V1 is equal to Vs, so Vs, and N3 by N1 is 1. As you increase this turns ratio, your voltage blocking capability of diode will increase, and you will be required to put the higher rated diode.
Sir, here also the switch rating is same as this VD3.
Uh, in this scenario, switch is closed. When switch is open, we will discuss that.
Yeah, we will have this same rating will appear.
Yeah, similar kind of expression will come. Because, yeah, just let me discuss that open circuit condition, then it will be convenient for all of us. Okay, so any doubt till this point? Otherwise, we will move ahead. So when switch was closed, we computed V1, V3, and one more thing, we want to compute the ripple in this magnetizing current, right? So del ILM during on is equal to Vs by Lm into dt. So it is similar to other thing. And during on condition only this Lx would be conducting, right? So Lx will have the voltage across this inductor, that is V2 minus V0, and V2 is nothing but V1 into N2 by N1, and V1 is again Vs. So just let me write in terms of expression. So del ILX on is equal to V2 minus V0 divided by Lx into dt, and V2 is nothing but V1 into N2 by N1 minus V0 divided by Lx into dt, and V1 is nothing but Vs. So when the switch is on, so Vs into N2 by N1, okay, minus V0 into d by f Lx. So this is del ILX on. I hope it is fine. Now, moving ahead, when the switch is on, we are still when the switch is on, switch current. Switch current will be equal to ILM, okay,
Plus.
plus the current flowing in the primary winding. So let me show that winding. So when the switch is on or closed, current will flow in this winding as well as in this winding. Recall from flyback converter, when switch used to be closed, then current was not flowing in this primary winding. Okay, because of the reason this polarity of voltage was different there. But here the switch current will flow through the magnetizing winding as well as primary winding. So we can write it ILM plus I1. Okay. Is there any doubt in this?
No, so but the thing is, okay, we'll proceed to this.
Mhm.
We have ILM component as well as I1, that is Vs into dt divided by Lm,
Yeah.
L, isn't it?
In you are talking about ILM?
Nine, I1,
I1. Okay. So
one will be that
if
is reflected from the secondary, isn't it?
yeah, that will be reflected from secondary. You are right. Yeah.
And that will be reflected from secondary when the switch is on.
When the switch is on. Yeah.
Okay, okay. We want to know the flux diagram of forward converter because it is
Definitely.
different. It is different from flyback.
Yeah, yeah, yeah.
Please tell that.
Yeah,
Yeah.
definitely. I will mention that graph.
Because as per the load, it is going to cancel from the primary side. I think so.
Yeah, yeah. We will discuss.
We'll discuss. Okay.
So yeah, so we was at that point when switch was open. Let me discuss
What
when
sir
switch.
was telling, sir? What
Yeah,
he was
so
telling?
actually we discussed that when the switch is on, let us see the circuit. When this switch is closed, S1, then what will happen? This current I switch will be equal to ILM plus I1.
I yes.
And I1 from where you will get? That will be induced from the secondary side. This diode will be closed and there will be I2 flowing in this side and I2 into N2 divided by N1. That should be your I1, this I1, right? Because this I1 is flowing here and this is I3 is anyway off.
Sir,
Yeah,
so whereas in flyback we will get only this IM right through the switch.
yeah, yeah. So that's the difference in both. So there, when let me collect that flyback circuit so that you will be able to see. See both the circuit here. This is flyback. This is flyback. Yeah. So when in flyback switch is closed, okay, then magnetizing inductance will flow through the LM, okay, and the same polarity of voltage will appear, okay, fine.
Okay.
But what happens? This V1 will be equal to this V2 into N2 by N1, and this V2 is negative, right? So because of that, the negative there are no current flowing through the diode during turn on period. We intentionally want there should not be any current flow during turn on period. That's what the purpose behind using flyback. And as soon as when switch gets open, when switch was closed, all the current should flow through the ILM and all the energy should be stored in the magnetizing inductance. When switch gets open, all the current or all the energy, first of all, this current will flow through this winding and this current will be induced on the secondary side, okay, so that it will transfer its energy to the secondary side. So basically, this current I1 was zero in flyback. There was no current flowing in this primary winding during when switch was on. Are you able to gather that point?
Yes, sir. Yes.
So it is basically the current transfer.
Yeah, current transfer,
This is the
current.
basic difference between flyback and forward. It is current transfer.
Yeah, you can certainly say in that manner. Yeah. Because if you are not able to see in that way, then what will happen? When switch is closed, V1 is equal to Vs, that is fine. And V2 will be equal to Vs into N2 by N1 in opposite polarity. So we are maintaining here negative polarity intentionally so that this diode should not conduct. And when this diode will see the negative polarity across its anode, then it will be reverse biased and no current will flow through the secondaries. So it will force no current on primary winding. So that's the reason behind that
Yes.
converter. Yeah.
You are giving reason why I1 is zero now.
Yeah, I am giving the reason why I1 was zero in flyback, not in
Yes,
forward.
flyback. Yes, in flyback when switch is closed.
Yeah.
Sir,
Yeah, go ahead, please.
uh, in forward converter, when the switch is off,
Huh?
when the switch S1,
Hmm.
I think we have completed the on time discussion.
On
Is there anything
time,
remaining, sir?
on time. This. Yeah. I just finished on period when switch is closed. I am about to start when switch is off.
Sir, this energy stored in this LM
Hmm.
uh, will dissipate, will get transferred to the source
To the
through this
source
D3 and
through D3. Yeah.
sir, at that time,
Huh?
if D3 need to be forward biased,
Huh?
then this inductor should have a voltage higher than the source at some point for some point to dissipate to discharge through the diode D3.
Quickly, you mean that's the question what other person asked, that we should increase the value of this V3 so that our current or energy through LM should quickly discharge. That's the same question you are asking, or your question
Ah,
is
yes,
different?
sir.
Yeah,
Yeah,
so
yeah. How V3 becomes larger?
how V3 becomes larger? No, V3 does not become larger as of
Then
now.
Vs.
No, no, no. Then VS. No, no, no. Because V3 by V1 is equal to N3 by N1, and we generally maintain N3 by N1 as 1. So V3, if you increase the value of V3, what was the side effect? That, you know, the endurance of VD was higher. Endurance of VD, as we saw, that was Vs plus V3. So as you will increase the V3, that will not only, that will just increase the value of rating of diode as well as the value of rating of switch also. We will see in just a while that how it will increase the value of voltage of switch, voltage blocking capability of the switch.
Yeah, across the switch it is okay, but across D3 we'll have only the forward drop across D3
Why
because it is
you are
conducting. When
saying
switch is
so?
off, it is conducting.
Okay, when switch is conducting, the
Switch is
volt
off.
when
S1
switch
is off.
when S1 is off, yeah, then yeah, then D3 will see only V3. Yeah, you are right.
So then if D3, then the LM that is suppose we have V3,
Hmm.
then V3 has to supply Vs plus VD3.
Okay, okay. So I think you are thinking far now. Let me finish the off period, then we will discuss this. Okay. What will happen during off period? Just we will see it first, and then we will take all the doubts. Okay.
Okay.
Because others might not be understanding that what question you are asking. So when switch is closed, sorry, open, what will happen that I am about to discuss. Your how D3 is conducting. Just let me. So it was the VS and it was disconnected through the LM. Here we have primary winding N1. Here it is N3, okay, and N2. Now, if this switch is off, let me finish it or let me remove it. Now, this switch is also open. So, our secondary side will not conduct. Okay, so let me remove this as well. There is no point, but there will be certainly one thing in secondary side that I will have to keep, that is your inductor energy will supply through the load, right? When your switch is off, and this is our LX, ILX. Uh, Remember that here diode is present, so now it is forward biased and it is sorted across the load. And here you have V naught. So on load side, your on load side winding or secondary winding will act as if it is a buck converter during off period. Okay. So now we have all the focus on primary side. So this N3 will see the voltage of Vs, right? So it will see the voltage of Vs and its polarity will be such that minus Vs, and here the diode was present. So let me show the diode so that we do not get confused. Okay, since it is connected conductively to the source side, so that I am indicating the polarity similar to the source. Otherwise, if it would have get induced, then I would have to write with the reference of dots. But as of now, it is connected conductively, so it is connected in that way. Now, this Vs will see here. I think something is wrong, so that let me. Is diode direction correct? Yeah.
Yeah, yes, sir.
Okay. So if okay, so this negative will appear across this cathode and positive will appear across this anode, and this N3 or this voltage Vs will be induced along the primary side. So V1 will be equal to Vs into N1 by N3 now, and let me write certain equations so that yeah, and since the dot is this polarity is according to the conductive convention, but since the dot is connected on negative side, so we will be talking in terms of this V3. Since once we assumed V3 as in this reference, so we will have to keep the same. Okay, so V3 we can write it as minus Vs. Okay, now since V3 has become minus Vs, and that will enable the forward conduction of diode, and V1 as I wrote as Vs into N1 by N3, and I don't think it is wrong, and I don't think it is right. Sorry, here it should be V3 into N1 by N3, and that will lead to minus Vs into N1 by N3. So this much voltage will appear here, V1, that will again be negative, and since our switch was present there, if you will apply the KVL with Vs, V1 and V switch, okay, so you will get V switch plus Vs plus V1 is equal to 0, and V switch will again have minus Vs plus V1. Okay, and V1 is nothing but V3 into N1 by N3.
Sir,
So
V1 will come in right hand side, no?
V1,
V
sorry,
is this VSW
hmm,
plus VS equal to VN now, sir.
is equal to V1, you are saying?
Yes, sir.
No, no, see, if you apply KVL,
Yes,
from negative to positive we are going,
yes, yes.
okay? From
Then
negative to positive here also, and here, okay, okay. So here
positive.
it should be V3. Okay, it should be V3. Mm, 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 mm. Sorry, no, 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 no. We switch plus Vs plus V1. Switch. No, no, no. Actually, you saw this Vs. I wrote with in this loop.
Right, which one, sir?
Yeah, V1 is the one.
Yeah. So this is right. And here
V1
V3.
is from plus to minus, no?
Yeah, see, we are going from negative to positive, and we are taking
Yes.
that convention as positive. So we switch plus Vs, right? Here also we are going from negative to positive.
Okay, sir.
Okay, you are saying that
From
mm,
plus
this
to
V1 should
minus
be
way.
minus. Okay, okay. V1, right. So V1 will be equal to V3 into N1 by N3, and V3 is minus Vs. So yeah, yeah, you are right. Sorry for the confusion. So V1 should be equal to V3 into Vs minus V1, and
Sir, actually we are trying to write the equation for voltage across the switch.
yes, yes, yes.
Uh,
Yeah, actually, she is right. If you see now, V3 is minus Vs, right? V3 is minus Vs, so it will come across that.
Actually, voltage across the switch is minus Vs minus V1. So
Minus Vs,
if we measure the
yeah,
switch polarity in
huh.
this,
Minus Vs minus V1, how?
yeah, because it is because the LM is now decreasing now because it is off. So V1 polarity will change.
Okay.
The top
But
side will.
yeah, but I am taking the reference what we have taken. Once we take the reference, we have to stick with that. Across the polarity, with dot, here dot is there. Wherever dot is there, we are taking positive polarity, right? And that we indicated with V1 and V3. So here we took dot and we indicated V1 as positive across the dot, and same we applied to tertiary winding, and across the dot we applied positive, right?
That is during on time now, sir.
So polarity will be same, no? Polarity, once we decided the dot, whatever the terminal will be dotted, that will be same. We cannot change that dot. The value will be changed, whatever it is happening here, but that dot will be same.
Sir, as per the switch, if suppose you are using MOSFET there instead of the generic switch,
Hmm.
uh, the, the other side should be positive, no, for it to block. The polarity of the switch should be reversed for it to block if you are using MOSFET there instead of the generic switch.
Yeah, that's fine. Let us suppose whatever whatever switch, even if you consider it diode also, it doesn't matter. It just
The drain should be connected to the, you know, so if you're using a MOSFET,
mm, it was
the
connected
source should be
upward.
connected to the negative of voltage source.
Is it correct?
Yes, sir.
Okay. Now go ahead. Yeah. So,
Yes, sir. Now for the voltage for the MOSFET to block,
hmm,
uh, the drain should be positive than source.
yeah.
So the right side terminal should be positive. Then yeah,
You're
that is
saying
the
this.
polarity for it to block.
Okay.
So to when the switch is off, this potential should appear across the switch. Will appear across the switch.
Okay.
Uh, so if such a polarity is applying,
Hmm.
then V1 and the magnetizing inductance should reverse so that Vs plus V1 will appear across the switch during off.
Yeah. V1 plus Vs. No, 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 no. See, you are misunderstanding this with your memory. So you might get confused with your memory. So see, what is happening if we you have watched the lecture and you might have remembered that V switch will be equal to Vs plus V1. That will come, that will come. You do not worry about that. Let us suppose if diode would be here, what will make a difference? Nothing,
If
right?
the diode will be there, yes,
Will
sir,
it make will it
the
make any
anode should be connected to the source of
yeah,
source negative.
Yeah. So it means
No, reverse opposite, sir, because it will conduct now. Don't block.
mm, cathode should connect to this negative polarity, right? Okay, to
Yeah.
make it off, you are saying, no?
Yes.
Yeah, to make it off, no, it is correct. To make it off, we have to apply such a polarity. Do you agree? To make it off, we have to make such kind of
Yes.
polarity.
Yes, sir.
This is V switch. Now you
Mm.
apply the KVL. It
If you
will
apply the
be
KVL, then uh,
Vs minus V1, right?
mm, okay.
You agree? Okay, so
Mm.
if you agree, then we can write V1 with V3, the relationship is nothing but the turns ratio, and V3 is equal to minus Vs, right? So minus minus plus N1 by N3. Now this might be the expression that you were remembering, and minus Vs 1 plus N1 by N3. The same was coming for diode. Let me see. The same was coming for diode as well. So VD3 so see in VD3 it was N3 by N1, and in switch it is coming N1 by N3, right? So basically what we do, we keep N3 by N1 not to overload any device. So as you increase the number of turns in tertiary winding, your switch rating will be decreased and your diode rating will be increased. So you have to do a trade-off there so that you will get proper kind of rating whatever you need. So this is a minor difference between the switch rating and diode rating. Okay. And let me draw the current waveform quickly so that we can finish it before time ends. So first we will draw ILX. Okay. So ILX would be similar to the conventional buck converter. If it is a continuous, then it will have characteristics like this. Here you have dt, here you have t. Okay, fine. I hope no doubt in ILX. This is your del IL. Now, the main thing about ILM, how will it vary? It should always start from, in a steady state, it should always start from 0 and it should die down before the starting of the next cycle. Okay, somewhere here. So this is the dt and this is your, let us suppose, some instant value t naught and this is your t. It will rise with the slope of Vs by Lm, okay,
Yes, sir.
and it will die down with the slope of, could you,
Vs minus V0
Vs minus V naught,
by
Vs
by
minus V naught into,
N2 minus.
okay, let me see the circuit here. So it should die down with this VLM should be equal to V1 my and V1 is V3. So no, it should not contain V0, it should be V3 by Lm. Am I right? V3 by Lm it should be.
V3 by Lm, because it is tertiary winding.
Yeah,
This
so
setting.
yeah, so when it will when the switch will be off, the voltage across tertiary winding is V3 and V3 is nothing but the Vs. And one more thing, it will die down across V1. Let me see. In this manner, this energy will flow or this current will flow and it will see the voltage VLM. If you will apply VLM is nothing but, if we will take this kind of polarity VLM, it will be equal to V1. Okay, do you agree till this point?
Sir, sir, can you hear me?
Yeah, go ahead please.
Sir, this LM, while discharging, it won't flow through the primary winding. It will flow through the tertiary winding.
uh, it will flow through tertiary winding, yeah, you are correct. And no, it will go through the primary and tertiary. See, it will go through this primary and primary is indirectly connected to tertiary. So tertiary is there so that its current will be induced to tertiary. Okay, our inductor current should induce to tertiary. Directly it cannot flow. So that, how to put it? Let me show you the circuit, equivalent circuit. Okay. Okay, see in this picture only, because if I will draw another picture, time it will consume lot of time. So see this ILM will start flowing and it will flow through the primary winding. Okay, and it will keep flowing in this manner, and this current will be induced to the whatever current is flowing in the primary winding, that will be induced to the tertiary winding. Okay, so here I3, it will be induced from its ILM and its magnitude will be, let me write, ILM is equal to ILM is equal to I3 into N3 by N1.
Yeah, yes, sir. So now the tertiary winding through the source and the diode, it will.
Yes, you got it. So yeah, so slope of this current, ILM, what I was talking. So ILM, sorry, V3 is equal to minus Vs, okay? And as if you see VLM, the voltage is appearing. Now again, see, there are two things, conductive and inductive. So now if we want to see the voltage across LM, so it must be whatever the voltage across this primary winding, right? VLM is equal to V1.
Okay.
VLM is equal to V1 and V1 will get its value from the induction. So it is all linked. So V1 will get V3 into N3 by N1. So let me write it V1 during this period. V1 is equal to V3 into N1 by N3. Okay. Now one more link is there. V3 now when switch is off is equal to Vs. Okay. Vs into N1 by N3. Am I right till this point?
Yes, sir.
Yeah, great. So the drooping slope would be Vs into N1 by
N1
N3
by N3 divided
divided
by
by
Lm.
Lm. Yeah, so that is the slope here. So it is Vs by Lm into N1
N3
by
by N1 by N3.
N3. So the more the value of N1 by N3, your slope will decay faster. But what it will create or where we will have to do the trade-off, it will increase the switch rating. So this is the switch rating. So as N1 by N3 increases, our switch rating will be increased.
Increase.
Okay.
Sir,
Yeah, go ahead.
And the diode rating will be reduced down.
Diode rating will be reduced now. So yeah.
sir, actually this drooping slope Vs, no?
Hmm.
Vs, the drooping slope should be in terms of V1, right? At least because uh, Vs is constant.
Yeah.
Vs is the source voltage, DC voltage, it is constant.
Hmm. Yeah, you are right.
Uh,
And Vs, where did we derive Vs? Vs from all the way from V1, right? VLM is equal to V1.
mhm.
See
Okay.
all the step. And when the session is finished, you analyze it on your own. Then you will find out that it is all linked. Try to visualize all the links here. It is a bit confusing since there are three windings that has been used in this circuit. So if you will sit in peace, then you will visualize. Okay. So similarly, flux will also flow here. The way of magnetizing component it is flowing in similar manner. Phi m is equal to Lm ILM. Okay. So as this ILM we drew in similar manner, the flux will vary, and flux should be zero before the starting of next cycle. Okay. So in next session we will start from this point, or we will try to uh, visualize, or we will try to compute the value of T naught in terms of parameters so that it should never violate the condition of the circuit. Okay, is that fine?
We will visualize the phi when the switch is on, and we will visualize the phi when the switch is off.
You mean flux in magnetizing inductance?
Magnetism. Yes, yes.
Okay, yeah, no problem. And flux will, the profile of flux will be similar as I stated here, but we will see it in more detail.
Because delta phi will be different than BDC.
VDC and delta phi.
BDC, magnetic flux density.
BM, what do you mean?
No, no, that is a DC value will be there for the CCM mode of forward.
DC
There is
value
going
of flux you are saying.
flux, yes, 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 and AC value of flux.
Okay, let me
Uh,
write it for my reference. DC value of flux,
mm,
AC and DC.
DC and AC value of flux.
Okay.
Mostly
Why you are saying DC value of flux? May I know?
DC value means whenever it is a CCM mode, we are having whatever the current shape delta IL,
Okay.
because we have considering that IM is going to flow and that is going to ride over the actual value of reflected current from the secondary, because
Okay.
it will having something like step value,
Okay.
okay, for delta IL. So delta IL is going to ride over the DC value of IL.
Let me clear it. Delta IL, you mean delta ILM or delta ILX?
Delta ILX, okay,
This one, delta
this
ILX.
ILX is going to ride over the DC value.
Ha,
This is
yeah.
ILM, no, sir. Yeah,
Hmm.
top one.
Yes, IL.
So you are saying that
This is going to ride over a DC value of IL.
IL,
Isn't it?
yeah.
And this is also going to flow in transformer, as well as this is going to flow in the inductor. Okay.
Okay, yes, yes, yes. I
And
got your point. Yeah.
then that it is to be clear what is that DC value, DC flux linkages, as well as and the delta BM, what we are going to use in the transformer, as well as we are using in the inductor. That
Yes.
has to be very clear.
Yes, yes.
Sir, this negative slope of ILX won't flow through this transformer, right?
Negative value of ILX will not
Negative
flow.
slope of ILX
Yeah,
No,
yeah.
that is going to flow through transformer,
for the diode.
not diode, as well as inductor. Inductor is going to conduct both the wave shapes.
In the next session, we will draw all the waveforms of current and flux, and then we will
Yes,
easily visualize. Okay?
yes, yes,
Yeah.
yes.
Okay. We will continue from this point only. We have
Okay.
written this point, so we will continue from this point.
So I want to discuss the transformer, flyback transformer design
Hmm.
in CCM as well as DCM, some steps.
Okay.
Then it is not clear to me.
Okay. Is it fine if we discuss it in next session?
Next session. Okay, okay, sir.
Okay.
This and that flyback transformer.
Definitely. Yeah. Okay then. Thank you. Bye everyone.
Okay, thank you,
Okay,
sir.
sir.
Thank
Good
you.
night, sir.
Good night. Good night everyone. Thank you.
Thank you, sir. Thank you, sir.